Hello everybody, welcome to lecture 16. So our theme today is the relation of similarity for matrices. This is section 3.3 of the lecture notes. So generally we're interested in linear transformations, and we're interested in describing linear transformations with respect to different bases. And the thinking behind that is that there may be a basis which is much more suitable than others for describing a particular linear transformation in terms of how the transformation behaves on the basis elements themselves that might elucidate what it does in general, for example, if it's a rotation or a reflection, something like that. Okay, so here's an example. And this is an example of a linear transformation from R3 to R3, which is given by left multiplication by this matrix A. That's its matrix with respect to the standard basis. And what that means is that the image of the first standard basis vector 1, 0, 0 under T is the first column of this matrix A. The image of the second standard basis vector 0, 1, 0 is the second column of A, and similarly for the third one. So the columns of A describe the coordinates with respect to the standard basis of the images under T of the three standard basis vectors. Okay, so let's give ourselves another basis. Let's let B be the basis with these elements B1, B2, B3. And one can quickly check that B is indeed a basis of R3 by confirming that these three vectors are linearly independent. In other words, if we make a matrix whose columns are these three vectors, the only matrix that goes to 0 when you multiply it on the left by that 3 by 3 matrix is the only vector is the 0 vector itself, 3 zeros on it. Okay, question. If we were to write the matrix of this same linear transformation with respect to the basis B, what would that matrix look like? Okay, so the matrix of T with respect to B, the basis B, should have as its three columns the vectors which have the coordinates with respect to B of the images under T of the basis vectors B1, B2, and B3. So it's not the same as the matrix with respect to T. And also this matrix A' of T with respect to B will then have the property that if we have any vector written in its B coordinates as a column, then multiplying on the left by this matrix A' should give us the B coordinates, not the standard coordinates, of the image of that vector under T. Okay. Remark here about the use of the term ordered is just to notice that a basis is usually referred to as just a set of vectors which is linearly independent. It spans the relevant space. But when you want to write coordinates of elements with respect to a basis, then you kind of do need to have an ordering for the basis. You need to know which basis element is considered to be the first one, the second one, the third one, so that you can write the corresponding coordinates in the right order. So if you don't have an ordering in mind for a basis, then you can't really interpret coordinates written with respect to that basis. So here we're interpreting B1, B2, and B3 as being respectively the first, second, and third elements of this basis for the purpose of writing coordinates. Okay, so how do we go about tackling this problem? Well, okay, to tackle the problem, we have to look at the vectors, the images under T of B1, B2, and B3, and figure out what their coordinates are with respect to B. And of course, we have a mechanism for doing that. We can sort of roll up our sleeves and write down the change of basis vector from standard basis to B, and kind of go through all the sort of technical steps there. But let's have a look at what these vectors actually are first and see what we come up with. Okay, so here are B1, B2, B3. We need to look at their images under T. With respect to the standard basis, what T does is multiply on the left by this matrix A. These are B1, B2, B3 written in their standard coordinates. So T of B1 then is the vector B1, which is 1, 0, 4, multiplied on the left by the matrix A, the original matrix A, and that means taking the linear combination of the columns of A with coefficients 1, 0, 4. So we get 1 times column 1 plus 0 times column 2 plus 4 times column 3. And when we look at that, we can observe that the result of that calculation is 208. The first entry is minus 2 times 1 plus 2 times 0 plus 1 times 4 and so on. Okay, now if we don't sort of rush ahead too fast, but just think for a minute about how to write 208 in terms of the basis elements B1, B2, B3, which are still written here in this slide, 104, 2 minus 10, and 0 minus 12. We might notice that 208, in fact, is just 2 times 104 plus 0 times each of the other two basis vectors. So it's just 2 times B1. So that's saying that the B coordinates of T of B1, the image of B1 under T, are just 2, 0, 0, 2B1 plus 0B2 plus 0B3. That means that the first column of the matrix of T with respect to B is going to be just 2, 0, 0. That's saying that the image under T of the first basis vector is 2 times the first basis vector plus 0 times the others. Okay, if we take B2, same story, multiply it by A to calculate its image under T. what we get is minus 6, 3, 0, and we might observe again that this vector is nothing but a scalar multiple of b2 itself. It is minus 3 times b2. Its entry in each position is minus 3 times the corresponding entry in b2 itself. So this is minus 3b2. Its coordinates with respect to the basis b1, b2, b3 is just 0, minus 3, 0. So the second column of the matrix of t with respect to b is going to be 0, minus 3, 0. Finally, b3 was 0, minus 1, 2. Image of b3 under t is the product ab3. That turns out to be 0, minus 7, 14. And sure enough, that also is a scalar multiple of the vector b3 itself. It's just 7 times b3. So its coordinates with respect to the basis b is 0, b1, 0, b2, 7, b3. And the third column of the matrix of t with respect to b is 0, 0, 7. So putting all that together, we can write down the three columns of the matrix of t with respect to b. Sorry, there shouldn't be a dash there. This is just b. And there it is. A dash is the diagonal matrix whose entries on the three diagonal positions are 2, minus 3, 7. And that is a nicer description of a matrix than the one that we started with. So A, the matrix of t with respect to the standard basis, is still written here 3 times, in fact, in the top left part of the slide. So we're saying the matrix of the same transformation with respect to the standard basis is this matrix A. With respect to the basis B, it's this diagonal matrix A dash, which is certainly a nicer thing than the original A, because it's much easier to deal with in terms of doing calculations with it, being diagonal. That's one important point. Another point, which is sort of equally important to think, is that when we look at the matrix A dash, we can sort of see clearly what A dash does to these three basis vectors, B1, B2, B3. It just multiplies B1 by 2. So it just sort of stretches by a factor of 2 in the B1 direction, multiplies b2 by minus 3, so reverses the direction and stretches by a factor of 3, and multiplies b3 by 7, so stretches by a factor of 7 in the b3 direction. So if we think of any vector written with respect to its coordinates, written in terms of its coordinates in the basis b, so it has a component in the b1 direction, a component in the b2 direction, and a component in the b3 direction, we can say exactly what happens to it under the transformation t. The b1 component gets doubled, the b2 component gets reversed and multiplied by 3 in terms of its length, and the b3 component gets multiplied by 7. But there's nothing as simple as that we could say from the standard matrix of t in terms of how it behaves on an element of R3. So this idea of being able to have a basis where the transformation has a nice representation is really quite a powerful one. Now, in this particular example, we started with the basis, which happened to be nice. We didn't know that. Well, you didn't know that in advance. I did, because I chose it carefully, but it wasn't obvious at first glance that this basis was special for that transformation. So of course, a question that we're going to look at is, if you just started with the matrix A, the transformation T, and not with any suggestion of what basis you might use, how would you find a basis akin to this one, for which the matrix had a particularly nice form, for example, being diagonal? Okay, but in any case, what this is saying is that for any vector v in R3, if we write the column whose entries are the b coordinates of v and multiply it on the left by this matrix A dash, which just means multiply the entries respectively by 2, minus 3, and 7, then what we get are the b coordinates of the image of v under t. Okay, that's an example, and it's a kind of nice one because it gives us a basis for which the matrix has a nice form. So how we can make sense of this in general and kind of describe what was going on there in general leads us to this matrix relation of similarity. So we're going to consider the relationship, using that example again, between A and A dash, but from another viewpoint. So if we write P for the matrix whose columns are the basis vectors of B, so B1, B2, B3, which are written here in the last slide and in the previous slide. So there they are. So write P for the matrix whose columns are these three columns. Okay, so from section 3.1, we know that the inverse of P is the change of basis matrix from the standard basis to the basis B. That means if we have any vector written in its standard form, its coordinates with respect to the standard basis, then multiplying it on the left by the inverse of P transforms it into its coordinates with respect to the basis vectors of B, B1, B2, B3. Okay, so this equation is worth sort of dwelling on for a minute, I think, to make sense of what it's saying. V on the right here is just the ordinary vector V, an element of R3 with its standard coordinates. This V sub B on the left is the column vector whose three entries are the coordinates of V written with respect to the basis B. Okay, so looking at this equation, if we can move it around, P is an invertible matrix. So if we start with the B coordinates, which is VB, this vector on the left, then the standard coordinates, just multiplying both sides of the equation on the left by P, are given by P multiplied by the column vector VB. So this is maybe hard to read, but just bear in mind, this VB is a column vector with 3 entries. P is a 3 by 3 matrix, so this is just a column. This is just a matrix multiplied by a column, so it itself is a column. So P itself, whose columns are the basis vectors of B, is the change of basis matrix from B to the standard basis. If you take the B coordinates of some vector, multiply on the left by P, you get the standard coordinates of that same vector. Okay, with that in mind, we can figure out in general what was going on between those two matrices A and A dash without having to go back to the linear transformation sort of every time. Okay, so suppose we were back at the first example and we only knew about A and we hadn't already calculated A dash, but we had a basis B, the one given to us in the first slide, with three elements, B1, B2, B3, and its columns form the matrix P. So to figure out what the matrix of T should look like with respect to that basis, just kind of algebraically, we can do it in a sequence of steps. So I really advise you, when you have a chance to sort of think on this and spend a little bit of time on it, to really kind of reflect on what's going on in this slide and compare it to what went on in the example. So if we want to figure out what the matrix of T with respect to B should look like in terms of the A and the P, okay, A is the matrix that we started with. T is left multiplication by A. So P is the matrix whose columns are the elements of the basis that we're interested in and that we'd like to write T with respect to. Okay, so the matrix of T with respect to B, it should take an element of R3 written in its B coordinates, multiply it on the left and give the B coordinates of the image of V under T. So what we have is a matrix A which operates on vectors written in their standard coordinates. So as a first step, we can take V written in its B coordinates, translate it into its standard coordinates by multiplying by P. Okay, so now P multiplied by VB, the B vector of V, is a column with 3 entries representing V in its standard coordinates. To apply T to that, the transformation T, we can multiply it on the left by the matrix A. Then we've got the product AP VB. Okay, this is still a 3 by 1 column, but it's the original VB multiplied by P and then multiplied by A. So this vector has T of V written in its standard coordinates because it was the standard coordinates of V multiplied by A. We want a matrix that will return T of V written in its B coordinates, so now we should multiply this one on the left by the change of basis matrix from the standard basis to the B basis. That's the inverse of the original P. So we should take this guy, multiply it on the left by P inverse. And what we have then is the vector whose entries are the B coordinates of TV. So overall, what have we done? We've taken V written with respect to its B coordinates. We've multiplied it on the left by the matrix P inverse AP. And the result of that is T of V written with respect to its B coordinates. So what we're saying is that the matrix P inverse AP is the matrix of the linear transformation T with respect to the basis B, where A is the matrix of T with respect to the standard basis, and P is the change of basis matrix from B to the standard basis matrix, and its columns are the elements of the basis B. Okay, so the conclusion is that the matrix with respect to B is P inverse AP, and indeed we could apply this to any basis P whose columns define some matrix P. There's nothing at all kind of connecting this argument really to the original example, except that the example was the context from which we started. Okay, so this is connected to some concept called similarity, which we have yet to define. So if F is some field, so the real numbers, for example, two square matrices A and B with entries in F of the same size are said to be similar if B is related to A by the fact that B is A multiplied on the right by some invertible matrix and on the left by the inverse of that matrix. So B is P inverse AP. So what this means in practice is that A and B represent the same linear transformation. If A is the standard matrix of some linear transformation, then B, P inverse AP, is the matrix of the same linear transformation with respect to the basis whose elements are the columns of P. So two distinct matrices are similar what it means geometrically is that they represent the same linear transformation with respect to different choice of basis. So remark, it's not generally easy to tell by glancing at a pair of square matrices whether they're similar or not. I mean, you might have some idea that they're not if you notice that they really have properties that are not at all shared. But generally, it's not easy. But there is one feature that they will have in common that at least can be easily checked. So the trace of a square matrix is the sum of the entries along the main diagonal from top left to lower right. And if two matrices are similar, they have the same trace. So if one matrix has trace 20 and the other one has trace 10, then you can say they're not similar to each other. If they have the same trace, it's not enough to make them similar, but it is one property that they would have to have in common in order to be similar. There are others, including the determinant, but we haven't talked much yet about the determinant. We are going to do so a bit later. So for example, similar matrices also have to have the same determinant, and we'll talk about that a bit more later. But just while we're on the subject, maybe I'll just say a word or two about why it is that similar matrices must have the same trace. So the trace, again, of a square matrix is the sum of the entries from top left to lower right along the main diagonal. And the assertion here in this lemma, which is proved in the lecture notes, we won't prove it in complete detail here, but we'll prove a version of it for 2x2 matrices just to see why it's plausible. So if A and B are n by n matrices, then of course we can look at the product AB and the product BA. Both of those are n by n matrices, and they are generally not the same matrix, but they do have the same trace. Okay, so the trace function is something that respects it doesn't care what order the matrices are multiplied in. These two matrices AB and BA are generally not the same as each other, but they do always have the same trace. And we'll see the reason for that in a minute. But a consequence of that, of course, is if you have some matrix A and you have another matrix that's similar to it, of the form P inverse AP, then you can apply this property of the trace function and say, okay, P inverse AP is the product of P inverse with AP. If I take the same product, P inverse and AP, the other way around, then I've got AP times P inverse, and that's just A because the P and the P inverse cancel each other. So if we believe the first dilemma, then the assertion that similar matrices have the same trace as each other follows from it that the trace of P inverse AP is always the same as the trace of A for any invertible matrix P. So why is this lemma true? Okay, so here's our lemma for a pair of square matrices of the same size, A and B, that the trace of AB and the trace of BA should be the same. So we're not going to prove this in full detail, although the detailed proof is in the lecture notes, and I really encourage you to have a look at it there, because what we're going to do is really exactly the same, except that we're going to make our life easy for ourselves by only doing it for the 2x2 case. But you'll see that the general case is really not any different. So if we give ourselves a pair of 2x2 matrices, I just write down some general entries for them. So if we write A to be A, B, C, D, where A, B, C, and D obviously can be any elements of our field, and write B to be a different 2x2 matrix with 4 different independent entries, X, Y, Z, W, for example, then the trace of AB is the trace of the product AB, and so it's the sum of the top left and the lower right entry of AB. So the upper left entry of AB comes from the first row of A and the first column of B, so it's AX plus BZ. And the top right and lower left entries, we don't even bother have to calculate them because they don't enter the picture for the trace. And the lower right entry of AB comes from the second row of A and the second column of B, so it's CY plus DW. So the trace of this matrix is AX plus BZ plus CY plus DW. So we can observe that it is a sum, of course, of pairs of products of pairs of things, each involving one entry of A and one entry of B. And the way that the entries get paired up is that on the main diagonal, each entry of A gets paired up with the entry in the corresponding position of B, so the A with the X. In the fourth term DW, we get the D being paired up with the W. So again, the second diagonal entry in each case. In the other two positions, we've got the B here of A meeting the Z of B. So the entry in the 1-2 position of A meets the entry of the 2Z of the 2-1 position of B in this contribution BZ, and the entry in the 2-1 position of A, which is the C, the second row, first column, meets the entry in the first row and second column of B. So basically, every entry of A sort of gets paired up with the entry which is in sort of the diagonally opposite position in B. In other words, if you took the transpose of B, then each entry of A meets the entry which would be in the same position of the transpose of B. So the lower left entry of the transpose of B would be Y. That Y meets the C in this expression for the trace. Why am I talking about that? Because that is really kind of a arrangement that doesn't change if you reverse the order in which B and A are multiplied by each other. And just to see that, so here's B and A again, the trace of BA. So if we look at the trace of BA, we'll find B and A, or BA and AB, don't have the same entries on the main diagonal. But again, BA has the property that when you look at all the entries on its main diagonal, you get all the possible pairs consisting of an entry of A and paired together with the entry that will be in the same position of B transpose. So each entry of A and each entry of B appears once in each expression. The trace of BA is the trace of the 2 by 2 matrix BA that comes from the top left. We've got the first row of B meeting the first column of A, and so that's XA plus YC. So sure enough, we can observe we've got an XA and a YC already in the previous expression. There's an entry in the top right and lower left that we don't care about because they don't impinge on the trace. And the lower right entry of BA comes from the second row of B with the second column of A. So that is ZB, second row of B and second column of A, so ZB plus WD. And again, we can observe that we have a ZB and a WD in the expression for the trace of AB as well. So the trace of BA is XA plus YC plus ZB plus WD, which of course, where these are just the entries here are just scalars, so they commute with respect to multiplication. So this is nothing but AX plus BZ plus CY plus DW, just to confirm that it's equal to the trace of AB. Okay, so that's the 2 by 2 version to make life sort of easy for ourselves, but the general version is no different, and you get exactly the same phenomenon that you get, if you take a 10 by 10 example or whatever n by n example, you get exactly the same thing, that the entries that contribute to the trace of the product of a pair of matrices just come from, it's a sum of products of pairs of entries, with in each case every entry of A and every entry of B appearing once, and the entries of A are paired up with the sort of transpose opposite entries of B. So that's how the trace of a product of matrices looks. Okay, so certainly a consequence of this is that similar matrices have the same trace. So if you have a pair of matrices that don't have the same trace, that is a sort of quick way of telling that they're not similar. If they do have the same trace, you don't know whether they're similar or not. Okay, a couple more remarks to finish off today, and then we'll resume next time. But in our example, we found that the 3 by 3 matrix A that we started with, which has long since disappeared, but it was your sort of typical looking 3 by 3 matrix. There it is from the start of the lecture. So there was A. And we found that it was similar to the diagonal matrix A dash, with diagonal entries 2, -3, 7. So just two things. The notation DIAG with some list of numbers is a standard notation in matrix theory for a diagonal matrix. So you just list the diagonal entries, and the entries away from the main diagonal are 0. So the other thing is that because A is similar to a diagonal matrix, the term that we use to describe that property is that A is diagonalizable. And we can also observe that the matrix which does the diagonalization job is the P whose columns were the B1, B2, and B3 of the basis B that we had in our example. So a diagonalizable matrix is one which is similar to a diagonal matrix. A diagonal matrix is one in which the entries away from the main diagonal are all zeros. Okay, so a couple of just interpretations of that, and this is where we leave it today, and then we'll resume next time. So from the diagonal form of A dash, which was the matrix of T with respect to the basis B, what it means is that T of B1 is the entry whose B coordinates are in the first column of the diagonal matrix A dash. So that means it has 0, 0 in the last two entries of the first column, and the first entry it has, as it happens, 2 in that example. But it's saying that applying T to B1 just gives us a scalar multiple of B1. So that the first column of the matrix just has a non-zero entry in the first position and zeros after that. Similarly, the image of B2 under T is a scalar multiple of B2, which means the second column of T has a non-zero entry only possibly in the second position and not in the first or third positions. And similarly, the image of B3 is a scalar multiple of B3, so its coordinates with respect to the basis B are just 0, 0, and then something in the third position, which could also be 0, but could not be as well. So What we're saying here is that each of the basis elements, b1, b2, b3, is mapped by the transformation T to a scalar multiple of itself. And we would say then that each of those is an eigenvector of this transformation T. So that's what it means to be an eigenvector. Okay, and again, thinking about it in terms of the matrix, what we know is that P inverse AP, where P is the matrix whose columns are the basis elements of B, we know that P inverse AP is A dash, and that's a diagonal matrix. And just tidying up that equation or rearranging it, multiplying both sides on the left by P, this is saying that AP is equal to P A dash. P is the matrix whose columns are the basis vectors B1, B2, B3. And A dash is the diagonal matrix whose diagonal entries are 2, -3, and 7. So when we say that AP is equal to P A dash, what we're saying is that multiplying the vectors B1, B2, B3 on the left by A is the same thing as multiplying B1, B2, B3 on the right by the diagonal matrix 2, -3, 7. The first column of that is just the sum of these three columns multiplied by it's just a combination of these three columns given by 2, 0, 0. So it's just 2b1. Second column -3b2, and the third column 7b3. On the other hand, the three columns of this version of the product on the left are just AB1, AB2, AB3. So we're saying that AB1 is 2b1, AB2 is -3b2, and AB3 is 7b3. So that B1, B2, and B3 are all eigenvectors of the matrix A. That means vectors which, when you multiply them on the left by A, give the same outcome as if you just multiply them by some scalar. So what we're talking about here is a basis consisting of eigenvectors of the matrix. So basically, the point of this slide is to observe that a matrix being diagonalizable is really equivalent to the statement that there is a basis of the space, R3 in this case, whatever it is, Rn or Fn, consisting entirely of eigenvectors of the matrix. So if you don't recall what an eigenvector is, or if you haven't looked at it recently, don't worry, we're going to recall all of that in detail next week, but this is just really where we're headed to, we're going to be interested in bases which consist of eigenvectors of matrices, and that will be the content of our lectures in week 9. So that's it for this one though. So thank you very much and see you next week.